Hello, and thank you for joining us. We are a team from the NASA SEA's Earth System Explorers program, and our project is titled Comparison of Land Cover Satellite Data to Globe Observer, utilizing Adopt a Pixel methodology toward the development of a novel citizen science observation system. This research was conducted by myself, Nandini, and my teammates, Sam, Jordan, and Neev.
So, what we've been working on over the last few months is citizen science, and citizen science is the field where ordinary non scientists contribute to the scientific community. And this is usually done through gathering data, but it is incredibly useful because not only does it bring scientific participation to everybody, it allows scientists to use a lot more information to get a better picture of our world. And a specific example of citizen science that we've worked with mainly is the NASA Globe Observer app, which is an online tool that allows anybody with a smartphone to gather environmental data, and it has a lot of useful features for comparing this data and analyzing it.
So the Adopt a Pixel 3 kilometer methodology breaks down a sampling area. So primary sampling units are photographed and classified via the Globe Observer app, and deconstructing areas of land in this way kind of allows for consistent ground truthing analysis. So the way we break up land in the Adopt a Pixel 3 kilometer methodologies, you have a pixel, which is the word used to define a unit of area used to describe spatial resolutions for remote sensing tools. So in our case, we're going to have a 3 kilometer by 3 kilometer pixel, and that can be broken down into sort of a 6 by 6 grid of primary sampling units, each with dimensions of 100 meters by 100 meters. And then there's a 37th primary sampling unit at the center called the centroid that is also 100 meters by 100 meters. And so the idea is that you can break down land in these different sections, different areas, and it allows you to compare that land to satellite data. So, in addition to our globe observations, we were also to collect and create land cover data from the following sources. EarthMap provided access to meta tree canopy heights, world cover, dynamic world, and land cover data sets. And Collect Earth Online is an online software that we use to subdivide our 100 meter by 100 meter primary sampling units into a 10 by 10 dot grid. We were then able to go in and manually assign land cover classifications to each one of those dots. We also used a Google Earth Engine app called Landsat Time Series Data, which gave us access to annual image chips from 1984 to 2025, and also greenery time series graphs. And then finally, we used ArcGIS, which is a geographic information system, which allows users to overlay information onto maps.
A great thing about this internship is that despite the fact that we are from all different parts of the country, we're all able to work together and share data to do this study. Sam studied the Washington, D.C. area. I studied New Hyde Park, New York. Neve studied Fremont, California. And Jordan studied Weslaco, Texas.
Myoi's Washington, D.C. has a complicated environmental history. It was originally built on marshland and then underwent major drainage projects, construction projects, river pollution cleanup efforts, and is now a national leader in urban sustainability through various environmental initiatives, including park construction and green roof construction. My AOI is centered at the Ulysses S. Grant Memorial on the National Mall, which covers the majority of central DC. Washington, D.C. AOI points and data comparison is what we have imaged here. On the right side, we have all of our side by side data comparisons, including globe observations and the additional data sources. On the left side, we have our entire AOIs mapped on top of the additional data sources to compare each of their resolutions. And then running along the bottom, we have the Landsat time series image chips, which gives us information on how greenery in the city has changed across the years 1984 and 2025. Here we've pulled some of that data out to look at agreement, partial agreement, and disagreement across the data. I like to focus on the disagreement, where we can see that in some sources of data, like the tree canopy, it shows a lot of trees, whereas other data sources like the SRI and Dynamic World don't show any at all. We also created an ArcGIS map. On my map, I have the Collect Earth Online primary sample unit land cover classification points, and the blue dots, which indicate the real locations of the globe images that I collected. And those are all mapped onto the world cover 10-meter data layer. This visualization of the collected data helps to compare satellite accuracy from world cover to our observations from Globe and Collect Earth Online.
The community I studied was New Hyde Park, New York. Originally a farming community, most homes in the area were built between 1940 and 1980. New Hyde Park is a suburban part of the New York City metropolitan area and in 2012 was affected by Hurricane Sandy. The Meta/WRI and world cover maps show a community with a mix of trees and developed land, while Dynamic World and ESRI predict that almost all land here is developed. This trend is shown in the 3 kilometer grid along with the smaller sampled areas. The Landsat chips and graphs show a consistent decline in tree cover over the last 40 years. An interesting observation I had was that while the tree cover was in general decline, a severe loss occurred in the early 2010s, indicating the impact of Hurricane Sandy on the community. One of the only points I found where the satellite data agreed was in a nearby pond. I was unable to perform a globe observation there, but all data in this chart shows the presence of water. A point of partial agreement was on the sidewalk of a busy street. The tree cover was relatively high from my area when I visited there, aligning with the world cover in Meta/WRI maps, but Dynamic World and ESRI still displayed all developed land. A point of complete disagreement was in a town hall parking lot. Every map was incorrect since the world cover and Meta/WRI underestimated the size of the parking lot, and the ESRI and Dynamic World didn't include the trees that were present. Looking at some ArcGIS maps and dashboards for our area that we assembled, the uploaded Collect Earth Online points that we manually sorted showed more diversity of land cover than the world cover data.
So, moving on to Fremont, California, it's a large suburban city in the heart of Silicon Valley where the recent population spike has seen it rapidly develop from marsh and farmlands into the bustling suburb it is today. And specifically, my area of interest is the northwestern part of the city. And looking at the compressed data, we can see a lot of red, which was the color symbol for buildings and homes. But if we also look closely, we can see a lot of the croplands and tree canopies, which are from the historic farms and wildlife preservations in the area. And here near the bottom of the slide, we can also see the timeline of the city changing from the open farmlands into the constructed area. And here we can see examples where existing satellite data were accurate, partially accurate, or completely inaccurate. And this is important because it reveals not only what data is right or wrong, but also the types and locations of the data that are commonly misrepresented. And this could potentially be analyzed in the future to resolve these types of errors. And finally, we can see the overlap map of my 3 kilometer by 3 kilometer grid, and all the patches of colored squares in the middle over here are the detailed analysis of high resolution images to actually see whether or not the lower resolution satellite images were accurate or not.
So now moving on to Wesco, Texas. Wesco became an agricultural hub in the early 1900s after irrigation systems were developed. It's well known for citrus farming, crops, and the 1015 onion. Since the late 1990s, the area has seen more urban growth but still holds on to its rural roots. My AOI involved parts of northern Wesco, which features a mix of farmland and neighborhoods and light commercial areas. Now, there is definitely a shift in northern Wesco. We are seeing that land is being converted into housing and infrastructure. The red on these maps are marking urban development. And I think this shows how fast Wesco is actually changing and why it is important to keep satellite data current. So I compared my Globe Observer images with satellite data sets, and in some cases, they all agreed, usually when the land types were vegetated. Partial agreement happened in areas that were changing, but in many cases there was disagreement, especially in areas where urban development changed croplands. So now moving on to area-specific challenges. So we had interns in Washington, D.C., New Hyde Park, Fremont, California, and Weslaco, Texas. So in Washington, D.C., interns faced challenges due to the presence of many federal buildings, of course. Security restrictions made that definitely difficult to take photos. Also, being that it is such an urban setting, it made it even more difficult to capture photos that didn't include personal identifiable information. So now moving on to New Hyde Park. One of our fellow interns noticed that local residents seemed very confused by their presence. Additionally, a few points fell on private property. In Fremont, private and government properties posed access issues. On top of that, the suburban layout made it hard to get to photos within the ideal range. In Weslaco, Texas, I personally faced a couple of challenges. Many of my AOI points were also located on private residential properties, but there was also a lot of ground conditions that didn't allow me to get to certain areas, such as tall grass or lots of overgrown vegetation.
So, analyzing some overarching trends across all of this data, we found that almost all of our areas of interest saw increases in buildings and urban development, which was paired with heavy decreases in grass and tree cover, which could be seen as concerning from an environmental preservation perspective. We also noticed that the European Space Agency's world cover mapping was the most detailed and most accurate from our data sources, especially compared to Dynamic World and ESRI, which were very low resolution and overgeneralized to not see the true diversity that was present within the different land cover types. And lastly, we noticed differences of large magnitudes between the high resolution pixel by pixel analysis of images, which was the rightmost column of those data compression charts, and the lower resolution generalized satellite classification, which was often very generalized and inaccurate.
So while the Globe Observer system and methodology were adequate citizen science and research tools, there's some serious pitfalls and limitations, including unintuitive user interfaces, low confidence in percentage slider land cover classifications imaged below, and a lot of image file lost during the upload process. Some interns, including Jordan on our team, lost up to 80% of their images after spending hours collecting them. And probably the biggest problem is the low resolution, as the Globe system compressed the image files to upload them to visual tools. Globe would compress these images to roughly zero point 0.1 megapixels. Modern iPhones take photos at about 48 megapixels. And so when you're losing that much information, it makes classifying land cover a lot harder. But the good thing is that citizen science can be improved upon. And that's what our team wants to do. That's where we want to take this research. So we've come up with an idea for a tool called EarthLens. EarthLens is a drone and app-based system that enhances land cover analysis and environmental monitoring through high-resolution data collection, real-time AI analysis, citizen photo uploads, data visualizations, and even collaborative features. EarthLens aims to build on and improve the Globe Observer's app citizen science goals. And this whole project is kind of based on what I just talked about, which is that the Globe application was really challenging to use effectively for a lot of users. The Globe photos uploaded to visualization tools lost a lot of valuable resolution, and negative user experiences prompted ideas and desires for a new and improved citizen science and cover observation system.
So now looking at the software part of EarthLens. So the software process is still in the development. So we're definitely looking to see if there's anything we can add. But so far, we have the ideas to use optimal tech stack for app development. We also want to build software for high resolution data upload that includes geotagging and satellite data overlays. We also want to develop a standard AI model native to the application to analyze observations and output land cover classifications. The real game changer will be the in app social networks to post photos, field notes, and questions to a community board. And this would make citizen science altogether more collaborative.
We plan on constructing a drone that has two 8 megapixel cameras for viewing the cloud cover and viewing land cover. And in addition to that, to have more data added to the database, we can have the Stella 1.1 and Heliostella devices All these will be controlled and have data recorded through a Raspberry Pi device, which can connect directly to the phone through Bluetooth. And in addition to that, we'll have an ESP32 on board, which will help control the motors for flight functions, GPS, and things needed for general navigation of the drone, which will also connect directly to the phone for ease of use.
So, putting it all together, EarthLens aims to be a project that is able to compare drone collected data points to satellite and globe data points in a novel way to maximize the accuracy of remote sensing land cover analysis and have the potential for us to scale in the future to analyze land cover using more robust data. We also want to create a new citizen science platform and a method available for both citizens and researchers to use to analyze the world around us. And why should anyone care? Well, EarthLens can democratize environmental science and observation while providing valuable data for researchers to assess disaster impact and the environmental change in our communities.
So we would each like to share a bit about our experience at Seas, and so we'll each give a few words of reflection. As my first real research experience, Seas really expanded what I thought was possible for my future. It didn't just build skills, it deepened my commitment to STEM, and inspired me to really pursue it in college and beyond. And that's why I'm really excited to continue working towards our Earthlens project goals as part of this really hardworking, committed, and really cool team.
SEAS was my first structured research experience after years of working independently, and it gave me the opportunity to explore earth science while learning more about my community. I'm excited to apply my engineering background to the research we're continuing in the coming months and help develop meaningful tools for citizen science.
So now moving on to my reflections. Seized helped me see just how powerful data can be when it is used to represent communities like mine. As I am from the Rio Grande Valley, I am also very proud of where I come from, and this project gave me the opportunity to connect advanced tools like satellite imagery and remote sensing to look at my hometown through a new lens. I am proud of the work our team has accomplished, and I'm very excited to see what we can accomplish in the coming months.
So for me, SEAS was an incredible program where I was able to take my previous experience in earth science, research, and engineering in order to create, analyze, and learn. And I'm super excited to see where my team's personal novel project goes and how I can continue this type of work in college and beyond. Thank you so much.
So before I send it off to Jordan to close out the presentation, we just wanted to share a few of the highlights that we've had throughout the SEAS program. So we wanted to mention the speaker series, from astronauts to long-range operations commanders and everything in between, as well as our extremely knowledgeable mentors. We've learned a ton from experts in the fields. Um, Team building workshops. So from real team science experts, we learned how NASA builds teams and got to put those skills and lessons to use, allocating responsibilities, using teammates' unique strengths and weaknesses, all to help in our really cool research. And then data collection, we gained firsthand experience with data collection and analysis, and through the Globe app, got to explore our own communities while doing so. This was a really awesome experience.
And finally, to close out our presentation for the day, we'd like to sincerely thank our incredible mentors, Rusty, Peter, Cassie, Andrew, and Bree, for their guidance, support, and encouragement through this experience. We are also deeply grateful to the SEAS program, NASA, UT Austin, and the Texas Space Grant Consortium for making this opportunity possible. We also want to take a special thanks to our peer mentor, Jeff, whose advice and leadership were essential to our success. Finally, thank you to our fellow interns. Your collaboration, creativity, and energy make this program the unique and enriching experience it is. Thank you.